Okay, so this last video will sort of wrap up the rest of Unit 19. So continuity and discontinuity. All right, so a function is continuous at a given point if and only if, first, the function exists, secondly, the limit as x approaches c exists, and recall that a limit exists if and only if its one-sided limits are equal. And so that negative, that's limit from the left. That would be the limit from the right-hand side. And then furthermore, both the function's y value and the limit's y value have to be equal in order for the function to be continuous. So when you're asked to prove continuity, it is a three-part definition. And so you would need to show all three of these pieces. All right, so let's look at the first graph. So condition number 1, f of x sub 0 has to exist. That works. Okay, that's that closed circle right here. Our second condition, the limit as x approaches x sub 0 must exist. So the limit from the left-hand side and the limit from the right-hand side both approach the same y value. So this condition is satisfied. But now notice from the graph, I mean, it's easy to see that it's not continuous because there's a hole on the graph. So the function is not continuous at x sub 0 since the y value of the function does not equal the y value of the limit. So as soon as one condition is not met, the function fails the rules for continuity. All right, next one, first condition. So we're checking out continuity at x is equal to 2. Okay, so continuity or discontinuity for that can only occur at one specific value of x at a time. All right, so first f of 2. All right, f of 2 exists. That's equal to 1. I look at that from my graph. Second, I have to look at my one-sided limits. Limit as x approaches 2 from the left-hand side. So on the left-hand side of 2, I'm approaching a y value of 4. Limit as x approaches 2 from the right-hand side. Now the graph on the right, my y value is approaching 1. So if the one-sided limits are not the same, I know that the limit as x approaches 2 of my function does not exist. Therefore, the function is not continuous at x is equal to 2. So from a graph, it's easy to see, okay, and I'll get into this later in the video, but a discontinuity is a break in the graph. So if I look at these, I'm tracing my graph, and once I get to this hole, I have to lift my pencil, jump over go away from the hole, and then I can continue graphing the function. On this second example, same deal. I have this upward facing parabola. I have to stop at that hole, and then I have to jump down to the other piece of the function. So it's easy to see graphically where discontinuity would exist. What I need you to understand is how to prove it algebraically, and that's the three-step definition. So now looking at this, if we do not have a graph, let's prove or determine if the function is continuous at the given point. So when you're looking at piecewise functions, you only have to check continuity where the pieces change. So according to piecewise, I have the graph of a parabola until I get to x is equal to 0. And then after x is equal to 0, I have the graph of another parabola. So first condition, f of 0 has to exist. So now when x equals 0, that's the quadratic on the top. So I would plug 0 into my top function, and I get an output of 1. Second condition, for piecewise functions, we always have to look at our one-sided limits. So limit as x approaches 0 from the left-hand side. Remember that from the left is values less than 0. So on the piecewise function, I'm looking where the intervals x is less than or equal to 0. So that's my quadratic with a vertical shift of 1. I replace x with 0, and I get 1 as my output. Okay, limit as x approaches 0 from the right-hand side. So now on the right-hand side, that's all values of x bigger than 0. So I'm going to plug that into my quadratic that does not have the vertical shift. 0 squared is just equal to 0. These numbers are not equivalent, so the limit as x approaches 0 does not exist. And therefore the function is not continuous at x is equal to 0. So again, you can only have a discontinuity at a specific value of x. So these conditions are when we're investigating a function at one specific value. Now we might be able to use it several times on a given set of functions, but you can only investigate one x value at a time. Okay, so now discontinuities, which I've really talked about already. Because if a function's not continuous, it has to be discontinuous. So discontinuities are any break on the graph of a given function. The easiest thing I can say to you to think about continuity is you can trace a graph with never having to lift your pencil off the paper. Okay, we trace left to right, a smooth and continuous curve. I never have to lift my pencil. If a discontinuity occurs, it has to occur at a domain restriction. And there can be multiple domain restrictions, but if your domain is all real numbers, you can't have a discontinuity because all real numbers says that there's no restriction on the value of x. So when we determine a domain restriction, we know graphically it's going to represent something. It's up to you to determine what they are. So every discontinuity can be classified as non-removable or removable. A non-removable discontinuity for our purposes is going to be a vertical asymptote on the graph. Direct substitution of the number will give us number over 0, because remember, discontinuities occur at exact values of x. So it has to look like something if I were going to plug the number into the original function. And when I get to the example, this last point will make more sense. But a non-removable discontinuity is a domain restriction that does not cancel. Okay, now on the other side, a removable discontinuity, graphically it's going to be a hole on the graph. If it's a domain restriction that I plug into my original, the output would be 0 over 0. And hopefully you recall this is our indeterminate form. We looked at this with limits, and to evaluate an indeterminate form, remember that we use factoring, we use the conjugate. For some problems, we looked at the graph. So we have to do something more to determine what that function value is equal to or what that limit may have been. So then removable discontinuities are domain restrictions that do cancel. So again, that does not cancel, that makes sense. That's our non-removable. And if a factor is going to cancel, that would be our removable discontinuity. So let's check out an example of this. All right, so when I look at, this is the same graph we already proved was not continuous, but this would be a removable discontinuity. And it occurs at x sub 0. Okay, so it's a hole. Right, I already talked about that. We can already see it. And if removable, all right, that didn't work. Think about it's removable because if I just simply filled in that circle, I no longer have a discontinuity. My graph goes on forever. Now the one on the right-hand side, I'm tracing my graph from left to right. Here I go. I have to lift up my pencil at this asymptote in order to get to the other part of my graph and trace this. So this would be non-removable at x is equal to a. For the same reason, if I think non-removable, there's no way that I can take that asymptote out. It's not like on the previous example where I was able to fill that circle in and now my graph became continuous. Now, algebraically, determine the domain restrictions of the given function. Classify each of those restrictions as removable or non-removable. Okay, so how do we determine the domain? Factor. So, factors of -12 that add to +4, +6, -2. 6 times -2 is -12. 6 minus 2 is 4. So remember our steps. Our steps were factor, determine the domain before you simplify. So my domain restrictions are any values of x that would put 0 in the bottom. So my domain x can equal -6 or +2. Back to my original. Now I can simplify, and f of x now becomes 1 over x minus 2. Okay. If I were just to look at this function and disregard the original, it appears that my domain is only that x can't equal 2. And that's why I need you to focus on getting the domain from the original problem. Now this is the importance of the canceling. So at x is equal to -6, some type of discontinuity is happening. At x is equal to 2, some type of discontinuity is happening. Why? Because they're domain restrictions. That's where discontinuities occur. Well, notice -6 is no longer, if I plug that into my simplified function, it wouldn't give me 0 over 0. It wouldn't give me 0 at all. So -6 is my removable discontinuity. And graphically, that tells me there's a hole at the point -6, comma, something. Well, think about where we can now plug that -6 back into. I can plug -6 now into my simplified function. So 1 over -6 minus 2. So -6, comma, -1/8. I'm literally going to have to graph a hole on the next slide. X is equal to 2. That's a non-removable discontinuity. So something I may have said in class is your non-removable are your domain restrictions that stay on the simplified form. So here I simplified my function, but if I think about 2 would still give me 0 in the bottom. And furthermore, if I were to plug 2 into the simplified function, I'd get that number over 0. So graphically, I know that I have a vertical asymptote at x is equal to 2. Okay, so now let's graph it. So f of x simplified to 1 over x minus 2. So all the parts about intercepts I can now take from my simplified function. So x-intercepts, there are none, because I can never set my numerator equal to 0. My y-intercept, when x is 0, y is -½ Our vertical asymptote, we already determined that was 2. Another discontinuity, we know there's a hole at -6, comma, -1/8. There's a horizontal asymptote at y is equal to 0. For this, you can either look at the simplified function or the original. It'll always remain the same behavior. In this case, bottom heavy. And now if we look at our sign analysis, really the only number I have to put on there are the vertical asymptotes and the domain restrictions that are vertical asymptotes. But I'll put both on there. If I take, again, into the simplified, -7, that'll give me a negative. I plug in 0, that'll give me a negative. I plug in 3, that'll give me a positive value. And this is going to make sense because this is the hole. All right, the only time my behavior is going to change around there is if the hole happened on the x-intercept. There is no x-intercept. All right, so let's graph this real fast. X equals 2. Y equals 0. Oh. 0, -1/2. I have a hole at -6, -1/8. Now the behavior works. Below the x-axis, I lift my pencil. And then to the right of 2, I'm